My name is Saurabh Kumar, and I'm on the marketing team here at H2O.ai. I'd like to start off today by introducing our speaker. Jakub, or Kuba as we call him, completed his bachelor's degree in computer science and master's degree in software systems at Charles University, Prague. As a bachelor's thesis, Kuba wrote a small platform for distributed computing on any types of tasks. During his master's degree, he developed a cluster monitoring tool for JVM-based languages, which makes debugging and reasoning the performance of distributed systems easier using a concept called distributed slack traces. Kuba enjoys dealing with problems and learning new programming languages. At H2O.ai, Kuba works on sparkling water. Before I hand it over to Kuba, I'd like to share a few quick webinar logistics. Number one, feel free to send us your questions throughout the session via the questions tab in your console. We'll be happy to answer them towards the end of the webinar. This webinar is being recorded. A copy of the webinar and slides will be available after the presentation is over. Without further ado, I'd now like to hand it over to Kuba.
Okay, thanks, Saurabh, for the introduction. So my name is Jacob or Kuba, and I'll be talking about sparkling water. So I will start with what is sparkling water about, and then I will move forward. What is the architecture of sparkling water? Explain it briefly. How we can scale sparkling water on different type of backends, and then I will move into the demo where I will demonstrate how we can productionalize H2O models using sparkling water on Spark, and then we will wrap it up, and I will be happy to answer your questions. So let's start. Thank you all for joining. So I was already introduced, so we can probably skip this slide. There is one tiny thing we didn't say. I enjoy climbing and tea. So what we are in Sparkling Water, we are a pretty small team. We are fully distributed team, the most distributed team in H2O.ai. I'm working in Prague, Czech Republic. Michal Malhava, the founder of Sparkling Water, he works in Mountain View, H2O headquarters, and we also have Mateusz. He works in Tokyo, Japan. So you can see that we are all in 3 different continents, but at the end, it actually works for us pretty well because all the communication we need to do regarding the projects we share online, so there is no hidden communication at all. So actually, being distributed works for us pretty well. So what is Sparkling Water? The name is pretty obvious. H2O and Spark. Why don't call it Sparkling Water? So what it is? Sparkling Water is basically seamless integration, transparent integration of H2O and Spark, where we want to give Spark users the ability to use H2O models instead of MLlib and ML platforms. So actually, people can still use Spark methods like Spark data munging, future engineering, but on the other hand, they can go into H2O and use our advanced, powerful machine learning tools. It's perfect for already existing platforms where people already have Spark deployed. Usually, like big companies and big customers already have Spark pipelines in use, and they already want to use. They are not happy for some reasons with Spark machine learning, so they turn into us and they ask us if we can give them powerful machine learning, but without changing their production pipelines. So we can actually use Sparkling Water for this. What are the benefits of Sparkling Water? So there is lots of benefits on the side of Spark and on the side of H2O as well. So Spark gives us additional algorithms which we don't have at the moment so far. For example, natural language processing. We are also catching up, but Spark is a bit more advanced on that manner in data munging. So if you want to clean the data, store the data, Spark can do. Spark offers more advanced functions at this point, but we are catching up in H2O. And it also offers powerful machine learning pipelines where people can actually specify the data transformations and modeling steps like inside of the one single pipeline, which can be exported and can be shared amongst different users and different data scientists. So that can be that's amazing thing for people to use if you want to share your code with different people, if you want to share your models independently on the language used, and so on. On the H2O side, we offer advanced algorithms like H2O, JBM, grading, boosting modeling, deep learning, k-means. So like lots of well-known algorithms. Those algorithms are implemented from scratch. So we don't use any libraries for these algorithms, and they were written to work just fine with our cluster, H2O cluster. So it's highly optimized to work in distributed manner. For example, JBM, we make use of all the H2O nodes, so we distribute the tree modeling. So basically, we try to parallelize as much as we can. We also offer different APIs for H2O and therefore for Sparkling Water as well. APIs for Python and R, and we also have a graphical user interface called H2O Flow. So how we can use Sparkling Water? There is lots of ways how we can use it. The simplest way how to use Sparkling Water is just to use Sparkling Water using the packages option when you start your Spark application. So what you just need to do to write dash packages and specify there the maven coordinates of Sparkling Water package you need to use. This is a bit outdated. Right now we have version 2.2.7. But it works in totally the same way. If you are not happy with using Sparkling Water with this option, you can always download the official distribution from our page, and we have a script prepared called Sparkling Shell, which will start Spark Shell with Sparkling Water libraries already included, or for Python and R as well. So right now, I would like to introduce 3 different use cases how Sparkling Water can be used in production. Let me just show the full slides, as that will be easier. So the first use case we can see is that we load some data and we use we perform the data munging in a Spark environment. Then we decided we would like to use H2O algorithms, so we need to switch data formats from Spark to H2O. We need to actually do the transfer of different formats because Spark and H2O both platforms are using different internal architecture how to store the data. So we switch to H2O, do the modeling phase there, and then at the end we can decide whether we do predictions in Spark or H2O. It's up to us. So this is the first use case. The second use case is that we can integrate the data munging and exploration phase together, and we can use both Spark and H2O like as much as we want. So we can switch as many times as we want between these 2 data structures. And once we're happy, we can go to modeling phase and again use H2O or Spark. And the use case I like the most is the first one. And we can see that on the top of the slide that we have some offline model training. And basically what we do is we use Spark for offline data preparation. We can also use H2O for that stage, and we train H2O model, and we can export that model in different forms. We have a free forms how we can export the models in H2O. One way is a binary model, which needs H2O runtime when we deploy it. But we have also 2 other forms which are called H2O Pojo and H2O Mojo. I will explain that in a bit in following slides. And these two model formats, doesn't need H2O runtime to be available. So it's perfect for deploying H2O models because, for example, on the next part of the slide, we can see that we take the model and we can use it in the stream processing pipeline. So we can, for example, have Spark streaming application which expects some data from web page or from some files which are created iteratively, and we read those files or read those pages, and we then send this data to H2O model for predictions. And we don't need to start H2O runtime in the streaming pipeline. So this is the advantage of like speed up and simplification. So I just covered like three different ways how we can use Sparkling Motor in production. And let me explain a little bit more what is Pojo and Mojo. So as I said, we have three different ways how we can export the models. The first one was binary model, and for that we need H2O runtime. It has dependencies on H2O, and it needs to be running. And the second one and third one is Pojo. Pojo is a shortcut for plain old Java object. And basically what we do, we export Java code representing that model. And what we need, just need to have a small library called H2O gen model, which contains like helper functions which we can use for predictions. And we can do predictions on this Pojo. And again, we can incorporate this Pojo in any Java or Scala application which we already have, for example, Spark. And we have also Mojo. It's a model object optimized. It's a different way how to store the model. It's not stored as Java anymore, because we hit some Pojo has some limitation. For example, if you have a really big models, it can exceed the size of the single Java file, which is not good. So we implemented Mojo, which is more efficient for three algorithms which stores the data in tree structures. And we can again use this. We can again do the same and do the predictions without H2O runtime. What is perfect on this is that we can even use Spark for doing the predictions, and we can do predictions in parallel. We can just give each Spark executor the Mojo, and Spark automatically will do the predictions in parallel, and we don't need to take care of it at all. And I will show that on the demo later. So sorry, I spent a bit longer on this slide, but I think it's important for us to understand that what is the difference between like binary models and Pojos and Mojos. So the next stage of this presentation is just feature overview. I would like to go over some major features of Sparkling Motor, how it can help us solving problems, and then I will go to architecture of Sparkling Motor. So one feature in what we have in Sparkling Motor is Scala that we can type Scala code in H2O flow. As I mentioned earlier, H2O flow is our user interface, and we have there so-called H2O cells where we can type like H2O commands, like give me all the models, train a model, train a JVM model. However, in Sparkling Motor, we implemented additional cell where we can type Scala commands, which is great for experimenting. If you don't want to like switch between flow and your shell, you can do everything in the flow. So you can access Spark context, Spark session inside H2O flow. The other feature is that we also can work with H2O frames as Spark data sources. This has several advantages that we can load. Basically, when something is Spark data source, it means that we can load data from it using like Spark Session API, which is really simplified API how we can load data from different sources. And it is also using advanced Spark query optimizer. So, for example, when we ask for number of rows, we don't need to load actually all the data. We don't actually load any data. We just count the rows. When we ask for just 2 columns out of 10 columns, we don't know all the columns, but just those 2 which we actually need. And so we are trying to be smart as Spark is and try to utilize the Spark API as much as we can to really play nicely with what Spark offers. The other feature, and actually it will be demonstrated in the demo, is machine learning pipelines. So what we are doing is that we are wrapping our algorithms so far H2O JVM and GVM and H2O deep learning inside of Spark transformers and estimators. Basically, transformer is concept where we can which encapsulates data transformations. So, for example, it expect one data frame on the input and one different data frame on the output, where the new one is transformation of the first one. For example, we can add a new field, we can cast some data types, and so on. And estimators, they wrap models. So basically, when estimator is called, it will train a model and produce transformer, which can then be used for doing predictions. This is perfectly explained on Spark documentation page. So if you would like to learn more about transformers and estimators, I would advise going there. And basically what we did, we just used these transformers and estimators and wrap our algorithms inside of these concepts. So it allows us to nicely embed our algorithms into Spark machine learning pipelines. And for Spark user, it has the advantage that they don't need to worry that much about if our algorithm will work fine in their pipelines. It will just work because we are using the Spark API. We can also save the pipelines. We can save the unfitted pipelines, so you can always train them on new data and create new pipeline model. Or you can even serialize and share the trained pipeline model for doing predictions. And again, for models which already has support for Mojos, GBM and deep learning already have Mojo available. We use Mojo underneath of this. So basically, if you use these pipelines, we don't use H2O binary models inside, but we use H2O Mojo models inside. So you can safely run predictions on these pipeline models without H2O runtime available. So the next thing what we have in Sparkling Motor and what we are offering to users is that we are integrating and exposing some Spark algorithms inside H2O Flow. So we are aware of the fact that Spark, ML, and MLlib offers more algorithms than we are, even though they offer more algorithms, and we would like to expose them in H2O Flow as well. So the user has the consistent experience of using Sparkling Motor. So they don't need to care about if it's Spark algorithm or H2O algorithm. So again, we can go to Flow and, for example, train Spark SVM support vector machine, use support vector machine modeling technique. And again, from these Spark algorithms, we can also generate Pojo and Mojo out of those. So you don't need, again, H2 runtime for these algorithms to run. So this is just internal demonstration how we expose the MLlib, algorithms in H2O Flow. So it's just technicality. We just create like some adapters and we hide the implementation so we can load the algorithms from both H2O and Spark. And so far I was talking in general about Sparkling Motor. And Sparkling Motor has APIs for 3 different languages, for Scala, Java, for Scala, Java, Python, and R. So for Scala, we use Sparkling Motor. For Python, we use PySparkling. And for R, we use RSparkling. So PySparkling is basically Python implementation of Sparkling Motor. PySparkling is available on PyPy, so you can just download it from there. Or it's the Python package is already available in the distribution we download from our page. It contains all H2O and Sparkling Motor dependencies. So we see that a lot. If you ever need to use PySparkling, you don't need to worry about other dependencies. You don't need to install H2O. You don't need to worry about Scala jar files. It's actually all wrapped inside. So you just need one single file containing PySparkling dependencies, which is already shipped in the distribution package or on PyPy. What you need to do is just to add it on your Python path, and that's it. Our scripts already take care about that. And what we did lately in this Jira SV341, that we made the PySpark distribution version independent. So basically, you can use it on any Python version which is supported by Spark at this moment. And we have also RSparkling. That's implementation of Sparkling Motor for R. it's based on Sparkly R package. So basically, we are using this Sparkly R package for communication with Spark, and on top of that, we build the Sparkly motor layer. And again, we are just using Sparkly motor exposed methods in this RSparkling. So it's basically tiny clients to Sparkly motor, and it's independent on Sparkly motor version and Spark. So basically, you can use it with any Sparkly motor version and Spark version you want. So that was that was three major languages we support. Scala, Java. I count those languages as one. Like basically all JVM based languages. Then Python and R. We can work on that in Spark and Motorboard. And other features. So just to wrap it up, we have also support for datasets in Spark 2.0. The datasets were officially released. Maybe it was 1.6, but I think 2.0 was for sure. So basically, we can work on RDDs, which is the original concept of data sharing in Spark. Then we also support data frames and datasets as well. We also have support for Zeppelin notebooks, so you can run Python PySparkling notebooks in Zeppelin. We have also support for XGBoost, so people can choose whether they want to use our implementation of H2O JVM or if they want to use our improved implementation of XGBoost. Right now, it's only available in local mode, but we are working on distributed solution, and it should be out very soon, I hope. We have also support for high cardinality fast joins. This is a feature implemented by Matt, our colleague, in Mountain View, and basically we can use this for really efficient data joining. Really, we can join millions and millions of data in few seconds, minutes. It's really good work done by Matt. We also support secure communication, so you can use Sparkling Motor in secure environments where you really need to configure Kerberos or SSL communication. And we have also support for sparse data. So right now we properly handle sparse data from Spark. So we don't, for example, we don't process all the data. We can smartly infer where are the data stored and on which columns and rows we need to work, and we try to be smart with regards to this, and lots of bug fixes. So upcoming features, we would like to expose more algorithms in Flow. Maybe we would like to expose Python cell in H2O Flow. So people can actually have Scala cell and Python cell available as well. We are working on integration with Steam, and the biggest feature I would say is more advanced pipelines with mojos, and basically exposing more algorithms inside Spark pipelines. For example, k-means and H2O AutoML. So right now I will talk over the following 5 minutes what's inside, and then we will go to demo. So what's inside? Right now it will be a bit more technical, so just bear with me. But I think it's important to understand how this behaves, how Sparkling Motor works internally, because it gives us better understanding how we can deploy it in different environments. So in Sparkling Motor, we actually have two backends. One backend is called internal, and the second one is external. When Sparkling Motor was developed, the internal was only one single option, but during the time we added the external backend. So basically, what the backend determines is where the H2O cluster is located, and each backend solution is good for different use cases, for different scale. So I will start with internal backend because that's the simple one, and usually people start with this one because it's really simple to use. So how it works in this mode? Basically, we have a normal Spark application. We have a Spark driver or Spark master in this case, and we have several Spark workers. We can see 3 Spark workers. And what we do is that in each Spark executor, we start H2O node. So basically, we create some sort of cloud inside of cloud. in each Spark executor, we start H2O node, and we let those H2O nodes cloud up, and they are still running inside H2O, inside of Spark Cloud, sorry. So this is easy for us because we don't need to take care about clouding process. It's handled automatically inside of Spark. We don't need to take care about configuring how H2O node should cloud up, where should we start H2O cloud, and how to connect. So it's really easy to start with. This is just another picture how we can see that. Basically, what we have the driver node and several worker nodes, and in driver node we have a Spark context class. It's basically main class used in Spark or Spark session in newer versions, which is used to orchestrate work and manage the computations in Spark. And on top of Spark context, we built H2O context, which is used for the same similar concepts, and we use it for managing H2O jobs and H2O modeling jobs and so on. And we build on top of Spark context. Important to say is that in this mode, we don't actually don't duplicate any data. In this picture, we can see data transfers because when we go from Spark data frame to H2O data frame and vice versa, it can be seen that we duplicate the data, but we don't have to do that because we live in the same JVM. So we have the advantage that we can touch the data directly without requiring us to copy the data somewhere because we live in the same machine, same Spark executor. So that's really advantage to us. And now, what is the advantages and disadvantages? What are the advantages and disadvantages of this solution? So big advantage is that it's really easy to configure and it's faster because you don't need to send you don't need to duplicate the data and you don't need to send the data to different cluster. It's already living inside of Spark cluster. And you don't need to transfer data anywhere because in Spark the computation is sent to the node, to the data. And disadvantage is that it's a bit more technical reason, but basically when we have a Spark dynamic allocation enabled or yarn preemption enabled, Spark can kill or join new executor, and basically that means for us end, because H2O can handle changes in the cloud shape. So when we start new executor, H2O would expect that H2O would be living there as well, but it doesn't. And when we lose some executor, H2O expects that this H2O node is still there, but it's not because the executor went down. This was actually compromised when H2O was being developed, whether to support high availability, whether to support if H2O go down, whether the cloud should reorganize and remain alive. But what the developers decided to do that don't implement high availability for now in favor of speed and accuracy. So that's a usual compromise what machine learning libraries and machine learning tools do, that they don't offer high availability and give users higher speed and higher accuracy. And it's really hard for us to implement, to tackle this issue on the implementation level, because there is no way how to discover all executors. Spark just doesn't expose any API how we can get this information. And this is what is solved by external backend. So basically, what is done here? That in this case, we are having two different clusters, Spark cluster and H2O cluster, and we just join them. We just wrap the communication between those two, so it can be used in the same way as the internal backend. And the advantage of this solution is that Spark executors can come and go, they can join and disappear, and H2O won't be affected because H2O is living in its own cluster, not Spark cluster anymore, but H2O cluster. And we can also start H2O cluster in case of YARN automatically. So it's really, we try to help the user as much as we can and do lots of manual work for them automatically. So how we achieve this? We just separate Spark and H2O, but we are preserving the API So it's completely the same as in internal backend case. You just need, when you are starting H2O, using the H2O context class, you just need to specify location of the external H2O cluster, and Spark Converter, the Spark cluster will connect to it, and then you don't need to worry whether if it's external or internal backend. You can use any commands you want, and they will work the same. In the yarn environment, you don't need to actually specify the location of the running cluster. You can tell the H2O context to create the external cluster for you, and it will create the cluster on your desired queue on yarn for you. And this is also the advantage that you can tune the resources a bit better, because H2O and Spark are independent and can be running on different yarn queues in separation. So you can configure the memory requirements for Spark and H2O, the core requirements. So basically, you have a fine-graded configuration for these two clusters. So this is how it looks on the picture. So we again have a regular Spark application. We have a Spark driver and several Spark worker JVMs. And what we can see that we no longer have H2O nodes inside of Spark executors, but we have their small stubs, which can come and go. We don't worry if those stubs die. And we have external H2O cluster, and those stubs communicate with the external H2O cluster. So we are affected by changes in cloud shape of Spark cloud shape. This is again another picture how we can look at the same thing, and we can again see that it's really external cluster separated from Spark. And pros and cons. The advantage is that we are affected by Spark executor going down and joining in, and we can configure the resources better. And disadvantage of this solution is that we need to transfer the data between Spark and H2O, between two different clusters. We are working on benchmarks at the moment, but from our experience, it's when it comes to really big scale, and you need to work on really big data and have lots of Spark executors, people tend to sacrifice a few minutes in terms of like having deterministic output. So that was the technical part of this talk. Oh, one more slide, sorry. I already covered that. So we have two modes in this external backend: the manual start mode, where we need to start the cluster manually and then connect to it, and the auto start mode, where the cluster is started for us. So this was the technical part of the demo of the presentation. And let me start the demo, the pipeline demo. So let me just go to shell and let me start the Jupyter notebook. So I just run this command. Let me just activate desired environment. So what I'm doing here, I'm just using this line starting a Jupyter notebook with Spark and motor features enabled. Let me make this a bit bigger so we can all see it. And let me open the notebook. I will be sharing with you. PyExamples, notebooks, Hammer, Spam, Mojo, IPNB. Okay, so we can see the notebook, and what I will be showing here is a Hammer Spam demo. So we're going to already see that kernel is ready. So it means that Spark is already running. And what I'll be showing here is a Hammer Spam demo. Where we try create a classifier which decides whether the message is spam or regular message. So let me just import the imports and check that Spark is running. Okay, so we can see that the Spark session is already running. I'm using Spark 2.2.1, so the latest one in local mode, because I'm running on my local machine. Now the next stage is to start H2O context. So again, we can use this simple API to start H2O context on already existing Spark context. If you are not sure whether you are using internal or external backend, you are always using internal backend. You will know if you are using external backend. For that, I would advise going to Spark and motor documentation and read a bit more there, how you can configure H2O with external backend. So we have a H2O running. We can see that it's running just for 7 seconds because I just started there right now. We have the flow URL, the extensions enabled in the H2O, and so on. And we have only one H2O node running in this Spark cluster because we are running in a local mode. I can open the flow, so we can actually see the flow. We can see the cluster status. So it's really nicely integrated. Right now, I will bring into scope one method which will just load the data for me. I will load a dataset called smsdata.txt, which contains 2 columns. The first column is the label, and the second column is the text, and the label specifies whether the message is ham or spam, and the second column is the text. And I just do simple pre-processing here. I remove the empty rows, and so on. And what I do right now, I will start defining the pipeline stages. Right now, no code will be executed. I will just define the stages. I will execute them at the end inside of the pipeline code. So the first step is to define the tokenizer. Basically, what I have as an input is the whole sentence, and I want to tokenize it, create words out of the whole sentences. So I just brought into scope this tokenizer stage, but it wasn't executed. The next pipeline stage is again Spark stage, and it's called stop words remover. And basically, I'm not interested in prepositions and words which doesn't bring any value to my model. So I can drop these words, and I take input column from the previous stage. Again, nothing was executed. This is just definition of this stage. So when it executes, it will take input from this previous stage, and it will perform filtering on those data. The next stage is that I need to hash the words to represent the words as numbers. So let me just bring this into the scope. I think I didn't run those, so let me just rerun these so we can be sure it's available. The next stage is actually Spark estimator, which is IDF, inverse document frequencies model, and it will create a model which represents how each word is how much each word is represented in a given corpus. So basically, what it does, it will train a IDF model on the input data coming from previous stage and create a model. So let me just bring it into scope. And the next stage is H2O deep learning. So you can see that the API is here the same. So far, it was Spark stages. And the next one is H2O stage, H2O estimator. And what we will do, we will train H2O deep learning model on the previous data. Really, the API is the same. I can bring into scope. I can specify all the options and arguments I want as in raw H2O. And the next stage, it's again sparkling water stage. It's a simple transform is that I want to remove helper columns, which I don't want to see in the final output. So I just brought that into scope as well. And let me. Actually, I have it twice here, so that's fine. Let me just check that this output is fine. Oh, it's actually completely the same. So I don't need to bring it to scope this one. So let me now define the pipeline. What this call does, I will just take all the stages here, and I will create one simple pipeline out of those stages. And then I can load the data using the helper method I defined right here. So I will remove empty rows, rows which doesn't actually contain any values, and create a Spark data frame out of those. And then I will fit the Spark data frame to the pipeline fit method, and it will create pipeline model. So let me run that. If I go to shell right now, I can see that the H2O deep learning model is already running, and it's training the model. So it will take a few iterations. We can see it here. It's performing the model training stage, and it's already done. So we have already pipeline model prepared, and we would like to try it out on on real data and tried some predictions. So what I'm creating here is spam method where I give it some text, the pipeline model, and threshold. I will create one Spark data frame and run transformation on this model. What this transformation does, it will go through all the stages again and perform the prediction at the end. So it will give us H2O deep learning predictions, and also all the cleaning and data munging features are run as well. What is nice about that if you give it whole Spark data frame and not just one data frame with one row, it will execute the predictions in parallel. And since we are using the Mojo inside of this pipeline, the H2O deep learning model is using H2O deep learning stage is using Mojo as a model representation. You don't need H2O running for these predictions. You still need to have H2O and Sparkling motor on class paths because of the classes, but you don't need to have it running. So let me bring the method into scope, and let me just try it out. So we have two sentences. Hey, Michal, H2O work party tonight in Mountain View. So that's probably not spam, but this second message seems like some ad which is usually which we can see that this seems like spam. So we can see that this model perform nice on these two simple sentences. And just to wrap it up, I would like to show that we can actually take this model and use it in production in Scala or Java on streaming data. So let me just export the model using this call. I'm exporting it as hammerspam.model, and let me save the scheme of data as well. This can be handy if you have like data with tens or hundreds of columns, and there is no way in streaming data how to determine the types of data. So this can help us a lot. And right now I already exported the model, and let me go to IntelliJ. Let me make this. Let me show it on the full screen. And let me make it bigger. So what this application actually does, it will load the model. It will load the model from the location I just created. It's Scala application. So right now I will load the model here. I will just load the schema here, and I will start reading some data files from as the streaming data, streaming input, and I will be processing them using the pipeline I just created in the Jupyter in the notebook, in the Python interactive notebook, and I will be writing the output on the screen here. So we can actually see that the predictions will be done in a streaming manner, and we can use the model which we train in Python in Scala. So let me start. Let me start the application. You can, of course, you don't need of course use IntelliJ for this. This is just nice and simple way how to present this. So let's just give it a second for Spark and all this code to initialize. So we can already see that it's running. And so far, I haven't started the streaming data to come. So no data there so far. And let me start the streaming. I have prepared like small script which will start putting files in the directory where this Spark application expects data. And we already can see that we are doing. It started to picking up those data files with the lines in it, and it started doing predictions in the output. So we can see the original label, the text message, and the prediction output, which contains the percentage, whether it's how probable is that it's spam or how probable is that it's ham. So that's it. You can see that it's really simple to use different languages, to use them together inside of the whole H2O platform and integrate all together. So let me just stop this guy and go back to slides. So it was the demo, and right now that's everything what I have to say to you. I hope that you enjoy the presentation and the slides. You can also see the slide with all the documentation and all the materials. So you can have a look on the YouTube where we have also videos. You can have a look. You can have a look on Stack Overflow, where you can ask us questions. We host lots of events if you visit our page in America and also in different parts of the world. So you are always welcome to join. And that's everything. Thank you. And now I would like to answer your questions if you have any.
Great. Thank you, Kuba. We have some wonderful questions in the chat window. Let's try to get most of them with the time permitting. The first question asks, does flow treat Spark data frames different from H2O data frames?
Yes, thank you. So basically, H2O Flow is a H2O-oriented user interface. So basically, everything there is oriented for H2O frames. In Sparkling Water, we brought Spark data frames into H2O Flow, but basically you can just you can list all the data frames in Spark, and you can convert the data frames to H2O flows. If you want to run any modeling or any data transformation in Flow, you need to have H2O frames available. But you can convert those in H2O Flow to H2O frames.
All right. Second question: can I use Scala or Spark in place of PySpark?
Yes. So basically, these two are both first citizens in Sparkling Water environments. So whatever you can do in Sparkling Water, you can do in PySparkling. So you can use the pipelines in PySparkling and Sparkling Water. Basically, it just depends on your preference whether you like Spark or Python or Scala or Java. I hope that answers that question.
Right. The third one is, we normally ingest data through PySpark and then convert a Spark data frame to an H2O or sparkling water frame. Our data sets are wide. In the brackets, they say thousands of columns is not unusual. So wondering if there's a way to convert a set of columns to a different data type at once.
Yes, that's a good question. So basically, we are not able to specify the data transformation when we transform data from H2O frame to Spark frame, or vice versa from Spark frame to H2O frame. We are able to tell it to change the type of the columns, because the transformation needs to have the information of the current columns and needs to perform the transformation at once. But you can always do the transformation before you transform the data to H2O or to Spark. So if you are in the Spark on Spark frame, you can map the frame. You can create a new data frame with new data types, or in H2O frame you can do the same. So basically, you can do that as part of the data transformation from Spark to H2O or otherwise, but you can do that in H2O or Spark. So it's like pre-processing stage.
Thank you, Kuba. The next question asks, how to map over data frame in Spark to extract raw data and make predictions using H2O Mojo model?
Yes, that's also a good question. So I would advise, if you need to do predictions using H2O Mojo, you can of course use the raw data and touch the internal API, but we already created Mojo H2O Mojo wrapper around this. So in Python, in PySparkling or Sparkling Water, you can load the Mojo model, and you will get some sort of H2O Mojo model object, and you can run predictions using this object, and you just need to pass its Spark data frame, and it will internally create the raw data and run the predictions. The advantage of this is that you don't need to worry about coding this, and it will also run in parallel automatically. But you can do that manually. But in that case, I would advise looking at the code of this object where it's implemented.
Very nice. Fifth question, do we need H2O for predictions when we use Mojo?
Yes, perfect. So I tried to stress it out that in case of H2O Mojo and Pojo, you don't need H2O to be running because it's H2O runtime independent. But what you need is to have some small H2O library or Sparkling motor library to be available on the class path because we need to have some classes available. In case of H2O, it's called H2O gen model, and in case of Sparkling motor, you still need to have a full Sparkling motor jar file on the class path. But it doesn't have to be running. So what you just need to have is to have Spark running and have the module available. Then you can load it and run predictions without H2O running.
When we transfer data from Spark to H2O or vice versa?
Sorry, can you please say again?
Pardon me. Is there any duplication of data when we transfer from Spark to H2O or from H2O to Spark?
Yeah, that's also a good question. And it's also important to understand that in case of internal backend, we don't duplicate any data because we live in the same JVMs, in the same Spark executors. And also Spark works in a lazy way. So we don't just take the data and copy it. When we need to perform some action, we just do the data transformations on the data when we actually need and on the part of data which actually need to be used. And we actually need to duplicate data in case of external backend because we have two independent backends which needs to be communicated together, but they don't share the same memory space. So in that case, we need to duplicate the data.
Great. The next question asks, from the demo, it seems the serialized model could be a pipeline that includes Spark transformations. Is that correct?
Yes.
And do we need to have Spark dependency to use the model in a JVM environment?
So the first part of the question, yes, that's exactly correct. What we did in the Jupyter notebook is that we were using Spark transformers and Spark estimators, so basically transformation stages, and the whole pipeline encapsulates the data transformations and the modeling as well. But for this, you need to have Spark running. You need to have a Spark dependencies and Spark running in order to run this serialized pipeline, because it's highly dependent on Spark. But what you don't need to have for running this H2O pipeline, this pipeline model is H2O runtime, because internally it's using H2O mojo, so you just need to have Spark, but no H2O for predictions. I hope that answered the question. Just otherwise, please let us know in the question panel.
Right. There's another question. Do you see data scientists going through the whole workflow, or will this workflow be scientists and infrastructure engineers?
So I think that for data scientists, the H2O flow is nice that they can experiment the data and they can quickly try the solutions. And then what we can do is prepare or in Jupyter notebooks, they are easy to interact with. And what we can do is export the model and share between data scientists, so they can experiment that in different languages what they prefer, because usually some people prefer Python, some R, some people, even some data scientists prefer Java. So we give them freedom what they can use, and when it comes to deployment, there are solid solutions based on JVM stack where people usually want to deploy things. So we can actually we integrate these two worlds. Data scientists can create a model, and they then give the model to engineers which can take the model into deployment in the JVM stack. Hopefully that's something what answers that question.
Yes. There's another interesting question. It says, what data sync issues can arise with duplicated data on Spark versus H2O? And how is the product set up to address such problems?
What kind of problems? Sorry.
As in, what kind of data sync issues can arise with duplicated data on Spark versus H2O?
Mm-hmm. Do you know just? I'm not familiar with the data sync term. Can you please just?
Data sync. As in, going from Spark to H2O and from H2O to Spark, can there be an issue with the duplicated data on either one of them?
I see. So basically, this transformations are done like we have. For the first thing to say, this is like the most tested thing in Sparkling Motor, because Sparkling Motor is built on top of this. So this is really highly tested. So the transformation is performing correctly with preserving. So it should preserve correct types and things so on. And as we mentioned previously, there is no data duplication. So for example, when we have a Spark data frame and when we need to create H2O data frame, we work in a lazy way, and we wait for the first we wait for the first action when we need to actually execute something, to just select few columns and then run transformation on those few selected columns. So far, like obviously there were also bugs in data transformations, but I think we improved that a lot. So I think it's nice. It's safe to say that it's behaving as it should right now.
Thank you so much, Kuba. Let's just quickly take one last question. It asks, is it easier to set up data exception handling diverging data flows using the Spark API or the Python API?
So I would assume that Spark API means Scala Spark API and Python API means Python Spark API. So in that case, those APIs are like equivalent. So again, it's just a matter of your preference, what you want to use. If you are more familiar with Python or Scala, both have some like advantages. Scala is more Scala has this type safety. In Python, it's easier to start with. So I would say it's a matter of choice. What do you want to use in a Spark environment?
Perfect. Thank you so much, Kuba. Before we wrap up here, I'd like to say thank you to everyone who joined us today. Again, a big thank you to Kuba for such a great presentation. And for the attendees, if you're in the Bay Area in the next 2-3 months, I'd love you to invite you to join us at a few upcoming conferences, including IBM Index SF in February, Strata San Jose and GDC San Jose in March. And for more information on our industry events and upcoming webinars, please visit h2o.ai/community. Thank you again. Have a wonderful day.
Okay, thank you all.